Can you see it?
Yes, we can. Go ahead and start.
Okay, so welcome everyone. My name is Adam, and I work with Konrad and Danny in Bergen, and we're mostly working on quenching theory and Monte Carlo development. In this talk, I'm going to focus on the jets and Parton showers in vacuum, and especially in their orderings. I will show some of our new results, some of our new showers, and some results of them. So, but before I start, let's ask the following question. If a single parton seems already simple enough, then why do we need jets? The reason is that jets are more than multi-parton objects. If you would like to have analytic consistency and precision, one actually has to use jets. The easiest way to see this is by taking one simple QCD splitting. It will have two divergences. The soft, when one of the daughter has a small energy, and the collinear, when the daughters are actually parallel. At high energies, like at RIC or at LHC, the enable phase space is big enough to get a bigger probability than one to split for a single parton. Therefore, one has to include the additional radiation to it. Parton showers are the analytical and numerical tools to describe this radiation, and therefore jets. They based on the simple QCD splitting from before, which has some properties. For example, the splitting angle or the relative momentum of the daughters. Parton showers iterate sequentially the splitting many times in a strict way following QCD rules. Based on this, one can see that jets are not simple multi-parton objects, but they are more like a single parton and all its additional radiation caused by the divergence structure of QCD. An important property of the splittings, and therefore Parton showers, are their scales. During each splitting, the scale strictly decreases. That's why we call them evolutional variable or ordering variable. But what is this scale? For example, it could be the virtuality of the incoming parton, just like in a radioactive decay. When you have an excited parent, it will decay to the less excited daughters with smaller virtuality. This was actually used in the first Monte Carlo implementations. Nowadays, it is more popular to use the relative momentum as an ordering variable because it is suggested by higher order calculations. Or in some other cases, people use angle as an ordering variable because of the knowledge about the soft gluon radiation. But all in all, they are almost equivalently good choices, and that's why we have different Monte Carlos. That's why we have different Parton showers with different ordering variables. Another thing what you can choose is the way of treating splittings. One of them, what I showed before, is the 1-to-2 splitting, which leads in the ultra parity splitting function. There is another way to do this, is the 2-to-3 splittings, when you actually split colored dipoles. And this is, for example, leads for the Catani-Seymour splitting functions, and it is like a more precise description. And again, different Parton showers use different splitting description, usually like the better ones or like the more precise one using the 2-to-3 splittings. To represent Parton showers, the Lund plane is a very good choice. Like one has to follow the hardest branch in the jet and plot the kinematics of the individual of the splittings. For example, here there's a splitting, it has an angle or it has a PT, and that's what you can plot on the Lund plane as a point. And if you follow the jet, then you plot this point. And by repeating this for many jets, one would end up in a distribution of splittings on the Lund plane. So For our work, for example, we implemented many parton showers. The first here is a PT-ordered parton shower. That means the evolution of the Lund plane was downwards, decreasing the transverse momentum of the subsequent splittings. As you see, the distribution is more or less like homogeneous, and the individual path for one particular jet is with the white lines. The next one is an angular ordered shower, which evolves from the left to the right, so decreasing the angle. And as before, the distribution is like homogeneous, very similar to the previous one, but the individual path is like in a different direction. I also implemented virtuality and the formation time ordering for parton shower, and these are evolving diagonally downwards, and the distribution, again, is very similar to the previous one. So all in all, there are 4 parton showers, and the individual path on the Lund plane in the 4 cases flows in a completely different direction. However, the distribution on the Lund planes are the same, and they're describing the same jets, like the distribution very similar. So like here comes the question that why we are interested in different orderings, and especially because I just said the distributions are very similar. So the reason is the following. When you have a hard scattering, you produce a highly excited parton. That is on a hard scale. On the detectors, you measure some ground state hadrons, which are at a low scale. And I just show that how parton showers do the evolution between these 2 scales. More precisely, parton showers with different ordering do this evolution in different paths. And here comes the complication. Because when you put an intermediate scale in between, then it could be sensitive to the evolutional path. Moreover, in our case, this medium scale is not only a momentum scale, but also it has a physical space-time boundary, like the size of the medium. Therefore, it can give some hint for the space-time structure of the jet, just like what we heard in the previous talks. Moreover, just like a short note, that this question also relevant in vacuum physics, where the intermediate scale can be something else. So just to sum up, this introduction part is that I showed what are like jets and parton showers, and I showed 2 choices what one could make in a possible implementation. One of them was the ordering variable, and another one was the treating of the individual splittings. And because of the interplay of scales, I argued that these choices could be relevant for both like heavy ion and vacuum applications. So because of this, and this reason, we implemented 12 new parton showers. All of them has like a flavor and energy momentum conservation. They have 4 different ordering variables, and there are 3 different ways of treating the splittings. We have the 1 to 2 splittings with the alternately Percy splitting kernels in a PTA 6 style. And we also have a recoiler style PTA 8 parton shower. And we also developed a full dipole shower with the Catani-Seymour splittings. And also to make some early medium prediction, we used the quenching weights, where we shift the energy of the particles, which splittings were resolved by the medium. So here comes some validation plots where we compared the PTA 8-like shower with blue and the dipole shower with green to the Sherpa results. So it is not important that what are on the axis, it is the differential jet resolution. The thing what I would like to show here is that we have a good agreement with the Sherpa results, also for more detailed jet resolutions. And usually like the dipole shower does a better job, of course, because it is a more precise description. If I have the PTA 8-like implementation of the parton shower and I turn on or I change the ordering variables, I have again like very similar results to before. Maybe the angular ordered is a bit different. And this is very similar to the dipole shower, what we implemented. So now let's say we trust in our implementation. So let's calculate the jet mass for example.
5 minutes.
Thank you. First, here's an analytical calculation on the jet mass in leading order and in leading logarithm. So the dotted line shows what if someone forgets to use the parton showers and stay at a single parton description. So in this case, actually a single splitting level. And of course, for like, so of course you will have some massive divergences in your calculation, but at high masses, it does a reasonable job because that's dominated by those splittings, those one splitting. But of course, it will completely fail the small mass properties like the peak. If we turn on the medium effect, the medium, this is still analytical calculation, the medium will suppress the high mass part, but the shape of the distribution will be the same because it's again just the single parton precision there. However, for lower masses, the peak will change, it will shift, it will be shifted, and also there will be some saturation because there will be splittings which are not modified by the medium. So here comes the Monte Carlo results. On the left, the PTA8-like parton shower with different orderings. What you can see, it's very similar to the leading log calculation. It has the peak. And what you can see also that at high masses, these different results are parallel each other. So like the distribution starts with the same slope, of course, because of the fixed order calculation. However, they have the offset because of the total normalization and the change in the peak. So like the different orderings actually will result differences in the peak. That's what we expected. And this is the same for the dipole shower. The fixed order part is relatively robust, but the peak and the shape of the peak actually changes. If I turn on the medium, here's just a reminder what we had in the analytical calculation. I get the following. So I have the suppression of the high mass part, which is again parallel to the fixed order calculation, like we predicted in there, and the peak moves to smaller masses, and there is some kind of saturation in there. And this is something very similar to the dipole shower. And you can see in this particular observable, like the jet mass, the different orderings actually lead like small differences, but that doesn't mean that there is no observable which is more sensitive to that, or let's say even less sensitive to this. So to sum up, that in this talk, I showed the inner uncertainties of parton showers, like the choice of the ordering variable and the way of treating the individual splittings. Based on the interplay of scales, I argued why these different choices can affect observables both in heavy ion and vacuum cases. And because of this, we developed 12 different parton showers that study systematically the differences between them. And it is a great news that our work made interested even the PP community, and the further results will come actually under the support of MCNet. And in the future, of course, we would like to get closer to heavy ion applications and improve our model with a more detailed medium description, but strictly like having the analytical understanding at the same time. So thank you for your attention.
Excellent, thank you. Our first question is from Raga from Wayne State. Even in vacuum, PP or E plus E minus, to what extent do different hadronization models smear the differences between shower implementations? This effect is only increased in the medium, right?
Yes, so based on the factorization, like once you apply a parton shower with different orderings, and then you apply the hadronization, like the total result should not really depend on this in vacuum. In medium, it is not necessarily true.
Okay, so the next question is something very similar from Ivan Vitev. Highly precise calculations have been done in SCET. The peak position and shape depends on non-perturbative effects. Have you studied how much the difference will survive?
No, I haven't. Actually, these results what I showed was so far without hadronization. But of course, we would like to have in an event generator hadronization. And in that case, we can actually study this in more detail. Yeah.
And then our next question is from Yi Chen from MIT. Do you plan to release the code or some generated samples?
Yeah, sure. Yeah, the full code is not available yet because these are so we're still working a lot on this, but of course.
Okay, so I'll use chair's prerogative. Have you considered possibly making this something that you could incorporate into the Jetscape framework?
Maybe it is like an early stage of this, but definitely we would like to make it in longer time accessible for sure. Yeah, for sure.
And then from James Mulligan from LBNL, can you comment on the comparisons between the different parton shower orderings and how the comparisons between the different parton shower orderings may change if you use NLO rather than LO?
I'm not exactly sure if I understand the question. So the LO and NLO, you mean the 1 to 2 and the 2 to 3 splitting difference? I'm not exactly sure in the question.
For the matrix element.
Oh, for the matrix element. Yeah, so in this calculation, it was like leading order. It should be not a problem to have next to leading order calculation, but so far I was talking about mostly like just jet samples, you know, and so we did not have, for example, a spectra of proton-proton matrix elements, but it should be not a problem. One have to do the proper merging, of course, and matching, but that's something what we're planning to do, of course. Yep.
Okay, so I think we're a little ahead on questions, but we take some time to do the switch. So I think that we will go ahead and thank you very much for this lovely talk, Adam. And we're going to move to our next speaker.